Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about a complete design of two-way restrained slabs by limit state method and according to the provision of IS 456-2000. So let us see what are the outcomes of today's class are. On completion of this class, you will be able to design by your own a two-way restrained slab which is resting over four discontinuous supports or four discontinuous edges. Here, when the four edges of slabs are discontinuous. Right. Let us recall the things what we discussed in previous class. In the previous class, we discussed about a design of two-way restrained slab when two adjacent edges of a slab are discontinuous. That means here two adjacent edge means one short edge and one longer edge of a slab are discontinuous, remaining two are continuous. For this case, we have designed a two-way restrained slab. So what are the design steps we have followed for designing of these slabs? First, we have to assume the effective depth. The effective depth based on Lx by d ratio, that is the shorter span to the depth or effective depth ratio, and that ratio should be assumed based on a stiffness criteria, right? And this depends upon the length of the span and given live load condition. If length of the shorter span is less than 3.5 and your live load is less than 3.3 kilonewton per meter square, then for a simply supported restrained slabs we can assume Lx by d ratio as 28. And if that greater than those values, say your Lx is greater than 3.5 meters and a live load is greater than 3 kilonewton per meter square, then we can assume the Lx by d ratio same as how we assumed for the one-way slab. Then we have to calculate effective length of the slab. This effective length can be calculated along the one-way x direction and y direction. That is, in x direction effective length is Lx, in y direction effective length is Ly. That can be calculated based on the criteria given in IS 456-2000. Here the two criteria are given. One is center to center distance between the supports is one criteria. Second one is a clear span plus effective depth. The minimum of these two criteria will be taken as a effective length for the particular direction of the slab. And then we have calculated we have checked whether our minimum depth required for given loading condition is sufficient or is our assumed depth of the slab is sufficient or not. That we have to check. It can be checked when if our assumed depth of a slab is greater than minimum depth required, then we go for the further steps. If not, we can modify the section and increase the assumed depth. Then we have to calculate area of steel. Area of steel can be calculated along x direction, y direction with respect to moment of resistance formed by tension zone. After calculating the area of steel, we go for checking of that. We have to check against the deflection, check against the development length, and check against the shear. And as is a restrained slab, we have to provide a torsional reinforcement. The torsional reinforcement is provided at this particular slab. That is, when two adjacent edges of slabs are discontinuous, we have to provide the torsional reinforcement at both the discontinuous edges which are meeting at particular corner. There we have to provide a torsional reinforcement, and we have to provide torsional reinforcement is at a place where one edge of continuous slab, one edge of slab is continuous and another edge of the slab is discontinuous. There we have to provide torsional reinforcement. And if both the edges of the slab is discontinuous, there is no need to provide the torsional reinforcement. And those are the amount of tension reinforcement, the spacing and diameter of bar, those we have provided based on the codal recommendations. Right? So let us start today's problem. The today's problem is based on when the four edges of the slabs are discontinuous. So what is the problem? A floor slab of a classroom of a clear dimension 3 meters by 5 meters is discontinuous over all four edges or all four sides of a slab. The corners of the slabs are prevented from lifting. What do you mean by this? So we can assume that this slab is corners are held down condition and we can say this is a restrained type slab. The slab is supported on a walls of width 250 mm and slab carrying a live load of 3 kN per meter square and floor finishes 1 kN per meter square. Use M20 grade concrete and Fe415. So let me explain the meaning of terms what we used in this problem. So the clear dimensions. So here we can decide, finally we can say that there is no effective dimension are given, only clear dimension are given. That is, shorter span direction is 3 meters, longer span direction is 5 meter, and it is discontinuous over the all four sides. That means it is with respect to case number 9 in our IS 456-2000 table number 26. According to that, we have to calculate the bending moments and quotient of bending moments. And here the corners of slabs are prevented from lifting. It is not free to lift, so it is prevented from lifting. So I can call it as a restrained slab. And it is supported on a walls of 250 mm width, and the live load given is 3 kN per meter square and floor finishes is 1 kN per meter square. Grade of concrete M20. From this I can write the characteristic compressive strength of concrete is 20 Newton per mm square and yield strength of steel is 45 Newton per mm square. So nowhere he is mentioned whether it is a one-way slab or two-way slab. So that can be judged by using the dimension of L shorter span direction, longer span direction. So to categorize the type of slab, we have a one condition that when Ly by Lx, or I can say longer span direction to the shorter span direction is less than 2, then we can call it as a two-way slab. So let us check here. Our longer span direction is 5 meter and shorter span direction is 3 meter. So 5 by 3 is equal to 1.67, which is less than 2. So we can design it as a two-way slab. The corner of slab are prevented from lifting, so we have to design it a restrained slab, and the case given is ninth case, that is all the edges are discontinuous. All four edges are discontinuous. So according to this two-way restrained slab will be designed. So let us start one by one steps. The first step would be assume the effective depth. We have to assume the effective depth based on the stiffness criteria. In two-way slab, if Lx by Ld value may be taken as follows as per IS 456-2000, when Lx is, that is the shorter span direction length is less than 3.5 meters, then live load will be 3 kN per meter square. Then for the type of support condition, we have to categorize the slab. If you are designing a simply supported slabs and if you are using a grade of steel is Fe415, then you can use it as a 28. If you are using Fe250, then that Lx by D ratio would be 35. And other condition, fixed slabs or continuous slab, the values will be like this. So let us check according to our given data whether which condition we have to use for calculating our Lx by D ratio. And here one more condition we have, if the case is reverse. If Lx is greater than 3.5 meters and live load is greater than 3 kN per meter square, then what we'll do? Then we have to take the Lx by D ratio same as have you assumed for the one-way slab. Let us check that condition, which condition we have to apply here. The clear span is 3 meters along x direction. The clear span along the y direction is 5 meter. Wall thickness is 250. Live load is 3 kN. Floor finishes is 1 kN per meter square. And FCK is 20 Newton per meter square, mm square. And Fy is 415 Newton per mm square. So now for decide the to decide the Lx by D ratio, we have to check our Lx value, that is shorter span value, and live load. Here the shorter span is 3 meters and live load is 3 kN meters. So I can say our shorter span direction is less than 3.5 meters and live load is equal to or less than 3 kN per meter square. As we are designing it is a simply supported slab, so we can assume for Fe415 steel we are using for this design. So Lx by D ratio for simply supported Fe415 steel grade steel is 28. So according to this we can assume that Lx by D ratio is 28. Based on that we have to calculate what is our assumed effective depth is. So effective depth equal to span by basic value, that is Lx by D will be actual value, and we want say D, so Lx by basic value. For this case the basic value will be 28. So D equal to span is 3000 mm generally given 3 meters, that will be converted into mms. So 3000 mm by 28, then D will be 107 mm. So I will round it out to 110 mm. Okay, then adapt a clear cover 20 mm and using 8 mm bars. So by using this condition, I am calculating what is the overall depth is. After knowing the effective depth, we can easily calculate what is the overall depth is. So overall depth can be calculated by using the formula small d, that is effective depth, plus clear cover. Here there should be a clear cover plus diameter by 2, that equal to 110 plus 20 by diameter is 8 by 2, that is 134 you will get. I will rounding up to 135 mm. So the second step would be calculation of effective span. As I already told you, we have to calculate effective span in x direction and effective span in y direction. So this can be calculated based on the codal recommendations. In code, he has given two criteria, that is a clear span plus effective depth of the slab. So the clear span is 300 mm and effective depth of the slab is already we have calculated, that is 110 mm. Altogether will get 3110 mm. And another criteria is center to center distance between the supports. So the center, that it is a clear span plus I have to take center to center distance, means we will have half width of the support at one end and another half width of the support at another end. Both half width will give me the one full width. That's why I am substituting here 250 mm is equal to one full width of the support. So 3000 plus 250 will give me the 3250 mm. So if now compare the values of criteria A and criteria B, the minimum of AB will be taken as a effective span length in that particular direction. So in these two, the minimum length is 3110, that would be considered as a effective span in shorter direction, that is Lx equal to 3110 mm. Similarly, calculate the effective span along the y direction. For that, I will follow the same criteria, that is clear span plus effective depth and center to center distance between the support. If I take the first criteria, the clear span plus effective depth of the slab, the clear span in y direction is 5000 mm plus effective depth is 110 mm, that equal to 5110 mm. And the clear distance between the center to center distance of the support is the clear distance plus the full width of the support, that is 5000 plus 250, that equal to 5250 mm. And I will have to check which value will give me the minimum value of a span in these two criteria. Here if I observe these two values, the minimum value is 5110 mm. So provide the effective span along the y direction Ly equal to 5110 mm. So this is how we calculate our effective span in x direction as well as y direction. So let us calculate the loads. So for calculating loads, we have to assume 1 meter width of the slab. So load means here three types of loads are there. One is dead load, live load and finishes. Dead load is nothing but the self weight of the slab, and that can be calculated by using this formula, that is overall depth by width and unit weight of the RCC. Generally the unit weight of RCC is 25 kilonewton per meter cube. If you substitute the values, the overall depth of the value is 0.135 meters and unit width of the slab is 1 meter. The unit weight of the RCC is 25 kilonewton per meter cube. If you multiply altogether, you will get 3.375 kilonewton per meter as a dead load. And live load given in problem is 3 kilonewton per meter. And the finish is also given, that is 1 kilonewton per meter. If we add all together, that will give me the total load. So the total load equal to dead load plus live load plus finishes. So dead load value would be 3.375 and live load is 3 kilonewton per meter and finishes given is 1 kilonewton per meter. So total load which is coming onto the slab is 7.375 kilonewton per meter. This is actual load which is I'd like to take up. But if any unforeseen loads are coming, for that we have to take you make use of the partial factor of safety. For loads, when you using combination of dead load and live loads, the partial factor of safety used for limit state of collapse and flexure condition, that is 1.5. So our total load must be multiplied with 1.5, then we'll get what is the factor load WU is. So 1.5 multiplied by total load is 7.375 kilonewton per meter. Finally, we get the total load would be 11.06 kilonewton per meter. That is the factored load. So after knowing the factored load, we have to calculate the factored bending moments, and the factored bending moments values are depends upon the type of edge condition given in the problem. So since the slab are supported on all four sides and its corners are held down, so from this I can say all four sides are edges of the slab are discontinuous. It is corresponding to the case number 9. So with respect to case number 9, if you see here, this is the case number 9 and all four edges of the slab are discontinuous. And if I draw the bending moment diagram for this, I will get along the longer direction, I will get like this, along the shorter direction, I will get like this. And there is no continuous edges along the left hand or right hand of the slab, so we'll get only positive bending moment along the y direction and x direction. So correspondingly, we'll get the positive bending moment coefficient. So we have only one x, alpha x positive and alpha y negative for this case. By considering those values, we have to calculate what are the bending moment along the x direction and y direction. So dear students, remember that here we have only positive x, alpha x here and positive alpha y. Why? So if you draw the bending moment diagram for this, only we have like this. So it will give me a positive bending moment at midspan. So the coefficient of bending moment will be positive. And for this case also, along the shorter direction, I will get a positive bending moment at the midspan. So the bending moment coefficient will be a positive. So based on these two alpha x and alpha y positive values, we will calculate what the bending moment is. So see, this is the table 26 of IS 456 2000, and this is corresponding to the case number 9. Four edges are discontinuous. Please make it correct. Four edges are discontinuous and positive moments are at the midspan. So for Lx, based on the Ly by Lx ratio, we'll get what is the alpha x value here, and from the Ly by Lx value here, we'll get the alpha y value here. See here, unlike your other conditions, here we have a positive and negative bending moment coefficients, and here we have only positive bending moment coefficient, because there is no, if you draw the bending moment diagram for this condition, there is no negative bending moment occur, so the coefficient of bending moment will not be a negative. That's why we have here positive bending moment values, positive coefficient of bending moment values, and along the x direction, and positive bending moment coefficient along the y direction. So let us calculate the design moments, the factor design moments. So here that is based on the Ly by Lx ratio. The Ly by Lx is 1.67, and here we have for this case. So we know the Ly by Lx ratio of 1.5 and 1.75. What is the alpha x value? But our value falls between 1.5 to 1.75. So we don't have direct value of alpha x. For that we have to go for interpolation technique. After interpolation technique, we'll get alpha x value is 0.075 and alpha y value will be directly we'll get, that is the ratio of Ly by Lx for this condition. The alpha y value will be 0.056 positive coefficient at the midspan along the xy direction. So that's why we have alpha y value is 0.056 here. So we know how to calculate the maximum bending moment or ultimate bending moment along the x direction and y direction. For calculating the ultimate bending moment along the x direction, we use this codal formula, that is alpha x into W into Lx square. So alpha x value is already known to you, that is 0.095 multiplied by W is 11.06 and Lx is effective length along the shorter direction, that is 3.11. So it is square means it is square, 3.11 square. So if you go multiply all these things, we will get 10.16 10 power 6 Newton into mm as a bending moment or the factored bending moment along the x direction. Similarly, the factored bending moment along the y direction, we have to substitute alpha y, W and Lx square. So alpha y is 0.056 multiplied by the factor load, that is 11.06 and Lx is 3.11 square. If you see, you will get 5.99 into 10 power 6 Newton into mm. Right. So after knowing the factor bending moment values, we have to go for check of minimum effective depth required. So minimum effective depth required can be calculated by equating our maximum ultimate moment to the limiting moment of resistance. Here the maximum value of which value you have to substitute as a mu here. Here we have two values of moments, that is mx and my in two direction. The maximum of these two value will be substituted as a mu here. So mu equal to k into fck bd square, and d can be calculated by using this formula under root of mu by k into fck b, and this k value will be depends upon the grade of steel what we are using here. In this condition we are using a k value Fe 415 steel, so k value would be 0.138. Now substitute the mu, k, fck and b value in this equation. We'll get mu equal to 10.16 into 24.6. It is the maximum value of bending moment along the x direction and among the x direction and y direction. The k value is 0.138. fck we are using is 20,000 mm is the 1 meter width of the slab. And if you calculate this, we'll get a small d, that is effective depth required. A minimum effective depth required is 60.67 mm. But assumed depth is 110, so our assumed depth is greater than minimum depth required for this particular slab. So we go ahead with the further steps. Right? So then we have to calculate area of main reinforcement. As we know that we have to divide our two-way slab along x direction, y direction into midspan and edge strip. Middle strip, edge strip, we have to divide along the x direction as well as y direction. So now we have to calculate area mid strip region along the shorter direction and area of mid strip region along the y direction, and similarly we can calculate area in edge strips also. So first we calculate along the shorter span, the width of the middle strip would be 1/3 of clear span in y direction. So 3/4 of clear span in y direction. So 3/4 of the clear span direction y direction is 5 meters. So width of the middle strip will be 3.75. For this meter 3.75 meter width, we have to calculate what's the area of steel provided. But that width of the slab we are considering for design slab is 1 meter. We are calculating area with respect to 1 meter. When we are providing in the slab, we have to provide it for 3.75 meters. So now MEX equal to 0.87 Fy ASTX D into 1 minus Fy ASTX by FCK into BD is the formula for calculating the area of steel along the X direction in midspan region, or I can say middle strip region. Now substitute MUX. MUX is 10.16 into 10 power 6 equal to 0.87 into 415 is Fy ASTX that we have to calculate, and 110 is the effective depth, and Fy is 415 ASTX is the that we have to calculate. FCK is 20. As we are designing the slab for 1 meter width, the 1000 mm is equal to 1 meter, and effective depth given is 110. And if we simplify this, we will get a quadratic equation in terms of AST squares. So that quadratic equation is 0 is equal to AST square x minus 5301.2 into AST x minus 5301.2 into 255.82. If we simplify this equation, we will get the area of steel along the x direction in middle strip region is 269.5 mm square. So after calculating area of steel in middle strip region, what is the spacing to be maintained for that? That we have to calculate now. So as we are using 8 mm diameter bars, spacing for 8 mm diameter bars for the middle strip region is equal to small AST by capital AST x into 1000. Here the small AST is area of 1 8 mm diameter bar, that equal to 50.3 mm square. As a circular in cross section, the small AST can be calculated pi by 4 into d square. Here d is 8 mm. So if you simplify that, we'll get 50.3 mm square. Now substitute small AST and ASTX already we have calculated. Then we'll get what the spacing is. So spacing equal to small AST is 50.3 by capital ASTX is 269.5 whole multiplied by 1000 will get 186.5 mm. So whether this obtained value of spacing is fulfilling the criteria given in IS 456-2000 or not, that we have to check. So as per IS 456-2000, spacing of main steel should not be more than 3 into D and 300 mm, or whichever is obtained. Among these three, the minimum value should be provided. See, the obtained value is 186.5 mm and 3D equal to 330 mm. If you substitute, the small d is 110 here, and another cutter is 300 mm. The minimum of these three values is provided as a spacing for main reinforcement in mid-span region, that is the middle strip region. So as we have the minimum value is 186.5 mm, we are rounding up to 180 mm, hence provide 8 mm bars at 180 mm center to center distance. So similarly calculate area of steel provided in a mid-span middle strip of y direction, that is the longer span direction. So before that we calculate what is the middle strip width in the y direction. That can be calculated by using the formula, that is 3/4 of clear span in x direction. So the clear span in x direction is 3, so 3/4 of 3 is 2.25 meters. And effective depth in y direction is effective depth in x direction minus diameter of bar, that is 110 is effective depth in x direction, and diameter of bar what we are used in 8 mm, that is equal to 102 mm. Right? So the area of steel what we are calculated, that will be provided in the middle strip region of y direction, but the area of steel what we are calculated here for 1 meter width of the slab, but we have width of the slab we have here in mid strip region is 2.25 meter. Correspondingly we have to provide the reinforcement actually in the slab, as though we are calculating 1 meter width of the reinforcement for 1 meter width, but we have to provide the reinforcement for 2.25 meters in middle strip region along the y direction. So let us calculate what is the area of steel provided in middle strip region along the y direction. That can be calculated from using this formula, that is MUY is equal 0.87 Fy ASTY D dash into 1 minus Fy ASTY by FCK into BD. Now substitute the values. MUY is the bending moment value, the factored bending moment value along the y direction, that is 5.99 into 10 power 6 equal to 0.87 into 415 into ASTY. The effective depth in along y direction is 102, and the substitute the remaining values here will get a quadratic equation. That quadratic equation is AST square minus 4915.66 AST minus 4915 into 66 into 162.65 equal to 0. If we solve this quadratic equation, we will get what is the area of steel provided along the y direction in middle strip region of the slab. So that is 168.4 mm square. For this area we have to provide what is the spacing to be maintained, as we are using same diameter of bar as we are used for x direction. So using 8 mm diameter bar, spacing can be calculated as equal to small AST by capital ASTY into 1000. Here the small AST is 1 8 mm bar diameter area. So for that small AST would be 50.3 mm square. So small s, because spacing for this direction is equal to small as is 50.3 by capital ASTY here, the 168.4 multiplied by 1000 will get 298.5 mm. So this obtained value should be checked with our codal provisions whether the spacing requirement is fulfilling or not. So we have to check here, and you have to provide the spacing between minimum of these three values. One value is obtained value and two values are given by code. As per code, the values are given for spacing is 3D and 300 mm, whichever is the minimum value we have to provide among these three. So 3D is 3 into 102, the 3D, so here D dash 102 is the D dash effective depth in y direction. If you multiply this, we will get 306 mm, and second condition is 300 mm. And among these three, whichever is the less we have to provide. So lesser value is 298.5 mm. So round off this figure to 290. Hence provide 8 mm bar at 290 mm center to center. So I think you are clear here the how to provide what is the area of reinforcement provided along the x direction of middle strip and y directional middle strip, and what is the spacing to be maintained for those two conditions. So after knowing that, we go for calculation of area of reinforcement in edge strip. As I already told you that we have to provide area of reinforcement along the middle strip regions and edge strip regions. So code suggests us to provide the area of reinforcement edge strip is, that will be a minimum area of reinforcement provided. The minimum area of reinforcement provided is depend upon the grade of steel as per code, that if you are using Fe415 steel, the area of steel, minimum area of steel provided is 0.12% of gross cross-sectional area. In this problem, we are providing Fe415 as a grade of steel. So AST minimum we have to calculate, that is 0.12 by 100, the B is 1000 and the overall depth is 135, then we'll get 162 mm square. So for this we have to calculate spacing. For this, in this region also we have to use 8 mm diameter of bar. For the 8 mm diameter of bar, the area of 8 mm diameter of bar, that is small AST, is equal 50.3 mm square. The spacing would be small AST by capital AST minimum whole multiplied by 1000. If you substitute those values, small AST is 50.3 and AST minimum is 162 whole multiplied by 1000. I will get 310 mm. And whether this spacing is fulfilling the criteria of your codal recommendations or not, those we have to check here. As per code IS 456-2000, the spacing of main steel should not be more than, in edge strip region, is 5D or 450 mm. 5D equal to 310 and 450 is another criteria. We have to check minimum value. This is 310 and it is 310 and 310, again we have 450. Minimum of these three will get, so 310 is the minimum, so we'll round it to 300. Hence provide 8 mm bars at 300 mm center to centers in edge strip in both the direction, as the X direction and Y direction. So this is how we calculate area of the steel in a middle span region and edge strip region along the X direction and Y directions. So with this, the design of a two-way slab, a restrained two-way slab, when the four edges of slab are discontinuous. Up to this is a design part. But the design members or the design parameters are whether they are safe against the deflection, or they are safe in development length, or not, we have to check. Before that, we have to calculate what the torsional reinforcement is. As we are designing a restrained slab, that means the corners of the slabs are not lifting off freely, so there may be a chance of occurring torsional stresses. Those torsional stresses are leading towards formation of cracks at the edges of or the corners of the slab. In order to counteract or to prevent those cracks, we have to provide torsional reinforcement in slab which are designed as a restrained slab. So as we are designing a restrained slab, there must be, we have to provide a torsional reinforcement. And the torsional reinforcement provision depends upon edge condition of slab. As we are designing slab with a 4 discontinuous edges, the area of reinforcement provided as a torsional reinforcement in each layer must be calculated by using this formula, that is AST equal to 3 by 4th of ASTX. So AST torsional reinforcement equal to 3 by 4th of ASTX is 269.5. So 202 mm square we have to provide. And on which the length we have to provide along X direction and Y direction, that is 1/5 of LX, another is 1/5 of LX. So LX is effective span, that is 3110. So you have to provide along the distance of 622 mm in X direction and Y direction. For the both direction, we have same distance we have to follow. The area of steel is provided is 202 mm square. This must be provided in 4 layers at corners with a discontinuous edges. So for this, I am using 6 mm diameter bars. The area of 6 mm diameter bar is 28.26 and spacing can be calculated is small AST by capital AST of torsion reinforcement multiplied by 1000. So small AST is 28.26 and capital AST T, that is the torsion reinforcement area, is 202. Whole multiplied by 1000 will give me the 139.9 mm. So hence provide 6 mm bars at a distance of 130 mm center to centers at 4 corners in 4 layers. Code says when we have a 4 discontinuous edges, at 4 corners we have to provide a torsional reinforcement, but each layer we have to provide area of reinforcement according to this formula is 202 mm square. And the spacing to be maintained is 130 mm center to center. The diameter of bar used is 6 mm. So now we check again is the deflection of the slab. So for whether our slab is safe against deflection, it has to fulfill the codal condition. Our values are codal condition values are depends upon percentage of steel what were used, and another is FS. FS is the stress under the service load. So a percentage of steel can be calculated 100 AST provided by B into D. AST provided is 269.5. That would be multiplied with 100 whole divided by 1000 into B. 1000 is the 1 meter width of the slab, and that will divide convert into mm, so it will be 1000 mm, and effective depth of slab is 110. So the percentage of steel is 0.25%. The similarly calculate stress in steel under service load, that we can calculate it by using this formula. F is equal to 0.58 Fi whole multiplied by AST required by AST provided. Here in this case both are same. So after calculating that and substituting the value, we'll get Fs equal to 240 Newton for mm square. So if your slab is safe against a deflection, it should fulfill this criteria, that is L by D maximum must be greater than L by D provided. So for this calculating L by D maximum, we want the modification factor value. This modification factor can be obtained by a percentage of tension reinforcement provided and based on the Fs value. So this value, if you see, the percentage of steel obtained is 0.25, that will be somewhere here, and our Fs value is 240. If you project onto the graph, so we'll get the values, it will intersect somewhere here. The value corresponding to this on y-axis is, so 1.5. From this case, the modification factor corresponding to 0.2% of steel and Fs equal to 240 is 1.5. So now calculate the your L by D maximum. L by D maximum can be calculated basic value multiplied by KT. For simply supported slab, the basic value will be 20 and KT is the modification factor in tension, that is 1.5. If we multiply these two values, we will get 30. And L by D provided, sorry, I forgot to mention the value here. So L by D provided is L effective is 3110 and effective depth is 110. So if you calculate, we will get somewhere around 27.7. So your 27.7 is less than 30. Hence we can say that our L by D maximum is greater than L by D provided. Hence okay, our slab is safe against the deflection. Next we have to check for development length. So development length value will be calculated. The check for development length will be if your slab is said to be safe against the development length, then it should fulfill the codal recommendation, that is LD is less than or equal to M1 by VU plus L0. Here LD is development length, M1 is the stress in steel at a maximum stress, that is corresponding to 0.87 Fi, and V is the factor shear force, L0 is the anchorage length. So M1 can be calculated corresponding to the maximum depth of neutral axis, that 0.87 Fi ASTX into 1 minus D, that is D minus 0.42 XU max. So XU max value will be for given grade of steel, that is Fe415, that 0.48 into D. D is here. Actually it would be 110. Sorry for that. It would be the D value is 110. If you calculate that, we will get the M1 value is 11.65 into 10 to the 10 power 6 Newton mm. The value will be less if you multiply it with 110. So this value will also go wrong. So it will get somewhere around 7.65. And the VU value is also will be wrong. So please student do it, correct it. And after assuming support width is 250 mm we have. So 250 by 2 into 8.5, that is 125 into 8.5 is I am bending the bar into 90 degrees. The anchorage length for every 45 degrees bent of length, the bent of the bar, the anchorage length will be 4 into 5. So we are bending into 90 degrees. So we have here 245 degrees. So 2 into 4 5 is 85. So 5 value will be here 8 mm. So 8 into 8 is 189. If you substitute that, you will get somewhere around some 650 or 700 if you substitute the correct value of mu. So our obtained value of LD is, LD can be calculated by using this formula, that is 0.85 5 by 4 tau BD. So the 376. So it is more than that. So I can say we are safe against the provided provision of development length. So let us see the summary of our design. So along the shorter direction, the width of the strip is 3.9 meters and the area of steel provided is along in midspan region is, that is middle strip region, 269.5 mm square, and we are providing 8 mm bars with a center to center distance of 180 mm, and width of that strip is 1/8 of clear span by direction, that is 0.625 meters. Along the shorter direction or along the longer direction, width of the middle strip is 3.12 meters, and the area of steel provided is 168.4 mm square. To provide 8 mm bars at 290 mm center to center, that is 3 meters, so the edge strip width is 0.375 mm. And these are the detailing of your a reinforcement edge strip, that is minimum area you have to provide, that is 162. So for that spacing will be center to 300 mm center to center, and area bar will, diameter of bar provided is 8 mm. So we are designing a restraint slab, we must provide the what is that torsional reinforcement. The area of torsional reinforcement is 202 mm square. This will be provided along a distance of x direction, y direction, that is 622 mm. That will be provided 6 mm bars at 130 mm center to center in the four corners in 4 layers. It will be 130, just pick it correct. And it is a detailing. So this is a slab which are having 4 discontinuous edges, right? And this is a 620 mm width along the x direction, y direction, as well as actual value 622, and we are providing 620 to round it figure. And this is the torsional reinforcement well provided in 4 layers, that is 6 mm bars, and area of steel provided is 202 mm square, and that is spacing will be provided in 130 mm center to center. So this is along your y direction, longer span direction. The diameter bar provided is 8 mm. The center to center distance between the longer direction is 300 mm. And the shorter direction and diameter bar used is 8 mm. The spacing will be used in 290 mm center to center. So this will be the cross section of this two-way slab. So that's all for today's lecture. Thank you.